Hello and welcome to our lesson on definite integrals. So we're going to start with the definition for what a definite integral is, and then I'll try to show you geometrically what's going on. So we're going to talk about a function, let's call it f, and let's say that this function is non-negative and continuous over a closed interval, and we're going to say the interval goes from some x value that is a to another x value that is b. If we draw in this non-negative continuous curve over this interval and we look at the area that is enclosed by that function, the x-axis, and the interval that we're looking at, then that area is what we're going to refer to as the definite integral from a to b. So when we're finding a definite integral, we are finding area. Again, it's an area of a region that is bounded by our function, the x-axis, and the lines x equals a and x equals b, which are the ends of our closed interval. That is the definite integral definition. So we have some notation. Because it represents area, we're going to say our area is equal to an integral. We know our integral symbol of our function that was differentiated with respect to x. The difference now in this notation is you'll notice that we have a and b here, which is the a and b from our closed interval. We're going to refer to a as the lower limit of integration, and we're going to refer to b as the upper limit of integration. Okay, so that's technically the definition. Now geometrically, let me show you what I just said. So let's say we have some function that is non-negative and continuous, so maybe it looks something like this. So here's our function f. Now what we want to do is look at this function over a closed interval. So let's say that this closed interval starts here at a and then stops here at b. When we're finding a definite integral, what we're finding is the area that is enclosed by the curve and the x-axis over this interval. So this is the interval we're looking at. The area in that interval between our curve and the x-axis, that area is a definite integral, represents a definite integral. Okay, so if I was to put this plainly in more plain language, the area between the curve and x-axis over the interval is a definite integral. Okay, so that is what we're doing when we're finding a definite integral. We are finding area. It's the area between our curve and the x-axis over a specific interval. Okay, so since this is a geometric thing, we're going to look at an example from a geometric approach, and then I'll show you why we actually need calculus in this. So for example, let's say I wanted to find the definite integral for y equals 2x over the interval from 0 to 3. Okay, I don't need any calculus for this. If my curve, my function is actually linear over the interval from 0 to 3, that's this interval here, then the area between that linear function and the x-axis on that interval is actually represented by this triangle. So when I'm finding my definite integral, if I'm just finding area, and my area is a triangle, again, I don't need any fancy calculus to find the area of a triangle. The area for a triangle is 1/2 times its base times its height, and I can see clearly here that the base of this triangle is 3 units in length, and that the height of this triangle is 6 units in length, so that my area would have to equal, it's really sloppy, sorry, my area would have to equal 1/2 times that 3 times that 6, and half of 18 makes 9. So we would say that the area is 9 square units, and that 9 square units represents the definite integral for that curve over that interval. Okay, so there it is. We found a definite integral. Now you can imagine that not every curve is a nice curve, not a linear function, right? When we are looking at a curve like this one, for example, this random one I drew in here, this area isn't going to be something I can find using a nice formula because this doesn't represent a shape that we have a formula for. So we have to have another method for finding the area when the geometric approach isn't really possible. And that's where the calculus comes in. In fact, the fundamental theorem of calculus is going to allow us to use integration to find our area. So a geometric approach, that's what we just saw a second ago, to finding that bounded area that we call the definite integral, it may not always be possible. Now, it's technically what we're doing every time, but we just can't always use some geometric formula to solve. So the fundamental theorem of calculus provides the calculus approach to finding that bounded area, and we are, in this fundamental theorem of calculus, evaluating our definite integral. So let me show you some notation, and then I'll tell you how it works. So the notation says, if we are trying to find our area, our definite integral, okay, then we're looking at, again, a definite integral that goes from some interval a to b of some continuous function, we'll call it f of x dx. When we find this area using our fundamental theorem of calculus, we're still going to find the indefinite integral the way we've been finding indefinite integrals. We're still going to integrate this function how we normally would. And we're going to get our antiderivative, which we call capital F of x. Now, after we do this, we're going to evaluate this antiderivative at the endpoints of our interval. And the notation that we use to say evaluate this antiderivative, this new function at b and a, is this. We use this bracket and we say, okay, evaluate this antiderivative at a and at b. And if we find f of b, again, evaluate that antiderivative at b, and evaluate at a, find f of a, and subtract those results, it will calculate that area for us. Okay? So we're going to find our indefinite integral the same way we have been finding indefinite integrals. And then we're going to evaluate that indefinite integral, that antiderivative, at the endpoints, at the upper and lower limits. And if we subtract those results, we are going to get the area that we are looking for. So let me go back up here and show you with this example where we already know the answer is going to be 9. Let me show you how the calculus works on this, and then we'll apply it where we actually have to use it, where we can't necessarily just use some geometric formula. Okay? So using this is a geometric approach here. And now we're going to use the fundamental theorem of calculus to get this same correct answer. The fundamental theorem of calculus, the calculus approach. Okay? So this approach says we're going to find the definite integral, in this case from 0 to 3, of our function, which was 2x dx. Okay, so this is going to get us the same area that we were looking for. So what we're going to do is we're going to integrate this. So we're just going to kind of ignore the upper and lower limits for a second, and we're just going to find our indefinite integral of 2x dx. So that's going to use our power rule. We're looking at 2x to the second. Remember, add 1 to the exponent and then divide by that new exponent, and then add our constant of differentiation. And because that divides out, we're just going to call this x squared plus c. So that's our indefinite integral. Now what we want to do is evaluate this at the upper and lower limits. So we're going to end up plugging in the 3, we're going to end up plugging in the 0, and then we're going to subtract those two results. So if I plug in the 3, I'm looking at 3 squared plus c. If I plug in the 0, I'm looking at 0 squared plus c. I want to subtract those results. So it's the upper limit first, the lower limit second, and then the difference between those two. So we end up with 9 plus c here, and then we're going to subtract 0, subtract c. 9 minus 0 is just going to be 0, and the c's are going to cancel. So there it is. 9 square units, the same area we just got a second ago, but using the fundamental theorem of calculus. So we find our indefinite integral, evaluate it at the upper and lower limits of the interval we're looking at, and then subtract those results. We get our area every single time, and that's particularly helpful again when the geometric approach isn't necessarily possible. Okay, now it's both times we're finding area every single time, so that's helpful to keep in mind. It's just not always possible to use some formula to do that. Alright, so now that we have this, one other thing, when we're finding our indefinite integral, we want to put our constant of integration there. But because we're going to end up subtracting the results of inputting these upper and lower limits, we're always going to have a plus c and minus c in this situation, so those end up canceling every single time. So often I will not put the plus c in here. Technically it should be there, but they're going to go away. Now I can do it because I know what's happening there, but it might be in your best interest to not leave off the c, because if you start leaving it off here, then when you go back to finding indefinite integrals, sometimes we get in the bad habit of leaving it off when it needs to be there. So it's up to you, but technically the constants of integration do end up canceling every single time. Okay, so let's look at some examples. Let's try to find some definite integrals. So we're in this one going to find the area that is bounded by the curve y equals 1 minus x to the 4th and the x-axis. So we have this graph. This curve right here represents the curve of y equals 1 minus x to the 4th, and we want to know the area that is bounded by that curve and the x-axis. So we are specifically looking for this area. I guess I didn't need to delete my highlights there. This is the area bounded by that curve and that x-axis. Now the geometric approach, again, not really going to work here because this is an irregular shape. We don't have a formula to find the area of this shape. Again, this is where the calculus is super helpful. So let's take the fundamental theorem of calculus and use it to find this area. So this area is going to be the definite integral from -1 to +1. So -1 to +1 of our function 1 minus x to the 4th. There it is. Okay, so we want to find our I gotta sneeze, I'm so sorry. We want to find our indefinite integral, so we can just use our power rule for each of those terms separately there. The integral for 1 is going to be x, minus the integral for x to the 4th would be x to the 5th divided by 5, and then technically plus c. So there's our indefinite integral, and now we want to evaluate that at the upper and lower limits, the upper, the larger number, being first. So I'm going to plug in the 1, so I'm plugging 1 in there, and I'm plugging 1 in there, and we're going to end up with, let's see, 1 minus 1 to the 5th over 5 plus c, and then we're going to subtract when we evaluate at -1. So we're going to plug in -1 minus a -1 to the 5th divided by 5 plus c. And then just be careful with your math, that's all. So this is going to be 1 minus a positive 1/5 here plus c. And then distributing here, negative makes that a +1. And then we have -1 to the 5th here, which will still be a -1. But that negative makes a positive. So this becomes a positive, but then I have to multiply by a negative, so it's really going to end up being a -1/5. And then the negative times the c, again, it's going to make those two cancel. So those are going to go every single time. So we have 1 minus a 5th, that's 5/5 minus 1/5, which is 4/5. I have the same thing here. 1 minus a 5th is going to be 4/5. So 4/5 and 4/5 makes this area 8/5, and we'll just say square units. So 8/5 is not quite 2, and hopefully that's a reasonable answer. If I said to find the area here, right? This would be 1 square unit, this would be 1 square unit, so 2 square units. We're just shy of that with the area that we've highlighted, so hopefully this 8/5 answer seems reasonable to you like it does to me. So there you have it, okay? So you could be asked the question in this way, find an area that's bounded by a curve in the x-axis, but the notation, when you see it, is asking us to do the same thing. So instead of all the verbiage there, oopsie, I did all this work and I forgot to delete it, we could just be asked to evaluate a definite integral, okay? So let's do it. Let's use our power rule. Now this is not x squared, but 4x plus 1 squared, so if this is u, then out here we need to have du, which should be the derivative of 4x plus 1, it should be 4. So since we need a 4 here, I'm just going to put it in, which means I have to also divide by 4. That way we're not changing the value of our function, and now we can apply our power rule to get our indefinite integral. So this is going to be, let's see, we have 4x plus 1 to the third power, oops, I forgot my 1/4. Bring down my 1/4, and then 4x plus 1, goodness gracious, 4x plus 1 to the third power divided by 3, and then we're going to have a plus c. I'm just going to clean that up a little bit. We're going to get 1/12 as our coefficient, and then our 4x plus 1 cubed plus c. So there's our indefinite integral. Now let's evaluate at the upper limit of 1 and the lower limit of 0. So plug 1 into that, and then plug 0 into that. So when I plug 1 in, we're looking at 1/12, and then 4 times 1 plus 1 cubed plus c. And again, if you want to leave the c's off, they're going to cancel, so it's fine. Just don't get in a bad habit of leaving them off when you're finding indefinite integrals and stopping there. All right, and then let's plug in the 0. So 1/12, and then 4 times 0 plus 1 cubed plus c. Okay, so over here, 4 times 1 is 4, and then 4 plus 1 is 5. 5 cubed is 125, and then we're multiplying by 1/12. So we're going to have 125 over 12 here, and then a plus c. And then here, 4 times 0 is 0 plus 1 is 1. 1 cubed is 1. Multiplying by a 12th means we still have a 12th there. So that's going to be a minus 1/12 and then a minus c. So again, c's are going to cancel. And 125 over 12 minus 1 over 12 is going to leave us 124 over 12, and that reduces by, let's see, 4. 4 goes into that numerator 31 times and into the denominator 3 times. So 31/3 units squared is our area. Okay, so hopefully you're feeling this. It's not so bad. Let's just go through a few more examples. We've so far focused on the power rule, but we have other integrating techniques. So here we're trying to integrate e to the 2x. So 2x not being an x there means this is a u, and that makes du 2. So out here we need du equals 2. So I'm going to stick a 2 out here, which means I need to stick a 1/2 out here, and now we can go ahead and integrate. So e to the u power, the integral of e to the u, is e to the u plus c. That's going to make this e to the 2x plus c, and that we're going to evaluate at the upper limit of 3 and lower limit of 0, subtract the results, and then we're good to go. So we end up with, if we plug in the 3, that's e to the 2 times 3 power plus c. And then let's plug in the 0, so e to the 2 times 0 plus c. And these look bad. So this is going to be e to the, why do my e's look so bad? E to the 6th power plus c. And then minus 2 times 0 is 0, and e to the 0, or anything to the power of 0, is 1. So it's going to be a minus 1 and a minus c. C's cancel, and so final answer is going to be e to the 6th power minus 1 units squared. And that would be the exact version of the answer. If you were asked to approximate that, a calculator would be super helpful. So e to the 6th power minus 1. Oops, that's not what I wanted to do. Is going to be approximately 402.43-ish square units, but the exact answer is going to be preferred if possible. Okay? Or actually, not if possible, because definitely it's possible, but if it's possible to type it into your assignments in Canvas is really what I mean to say, because sometimes we get some radicals that are hard to put in there, and so I might ask you for an approximate answer, so be prepared for both, but the exact answer is preferred. All right. Let's try another one here. So when we're integrating 1 over x, remember that's going to get us a natural log of x, and it's just x, so I don't have to worry about any u and du stuff. So the integral for 1 over x, again, is going to be the natural log of the absolute value of x plus c. We want to figure out this value at 1 and at 2 and subtract those results. So we're going to plug in the 2. That's going to be the natural log of, well, the absolute value of 2 is just going to be 2 plus c. And then from that, we're going to subtract the natural log of 1 plus c. And so this is natural log of 2 plus c minus the natural log of 1 is just going to be 0. Remember, natural log is base e. So natural log base e of 1 is asking e to what power produces this argument of 1, which means it has to be equal to 0. Hopefully that's a rule you remember from college algebra. So this is just going to be, what did I say? Natural log of 1 is going to be 0 and minus c. So those cancel. The natural log of 1 is gone, which means final answer is just the natural log of 2. Again, square units for our area. And that would be easy enough to type in, but again, if you were asked to, you can use a calculator to approximate this. The natural log, and you can also verify that the natural log of 1 is 0, but we want approximately how much is the natural log of 2. It's about 0.693-ish square units. Okay, so either answer is fine, it's just that the exact is preferred. All right, so we got some power rule in there. We have e to the u. We have 1 over x. Let's get a radical in there because I know how much everybody loves radicals. So I would start by rewriting this, of course, like I always do, as the integral from 1 to 4 of -3 times x to the 1/2 power. I don't know why I put parentheses there. Not wrong, just not necessary. Okay, so we can use our power rule. This is going to be -3 x to the, add 1 to the exponent, so 1 over 2 plus 2 over 2 is going to be 3 over 2. Divide by that new exponent, 3 over 2, add the constant of integration, and then dividing by 3 over 2 is multiplying by 2/3. So if we have -3 and we multiply by 2/3, those are going to cancel and leave us a -2. So this becomes -2 x to the 3/2, and I'm actually going to put that back in radical form, because I think it'll be easier to evaluate. So -2 times the square root of x cubed plus c is what we need to evaluate from 1 to 4. Alright, so let's plug in the 4. -2 times the square root of 4 cubed plus c. And then from that we're going to subtract -2 times the square root of 1 cubed plus c. So 4 cubed is 64, and the square root of 64 is 8. -2 times 8 is going to be -16. So we have -16 plus c. And then 1 cubed is 1, the square root of 1 is 1. 1 times -2 is -2, but multiplied by this negative makes it a +2, and then a minus c. So we're left with -14 plus, or -16 plus 2, which is -14 square units. And I don't know if any red flags are going out for you there, but we just found an area under this, or between this curve and the x-axis over this interval, and we got something negative. How can area be negative? Well, it can't. Area can't be negative, but because we're on a graph where certain locations are represented by negatives, we could end up with negatives. So negatives really are just location things, and that happens in this particular problem because the interval of graph we're looking at happens to be below the x-axis. Let me just show it to you here. If we're looking at negative 3 times the square root of x over the interval from 1 to 4, you can see it already, but 1 less than or equal to x less than or equal to 4. So this is the little piece we're looking at here, that area, so that little area that's enclosed, that's the area we just found. We got it to be negative because it sits below the x-axis, okay? So this is negative because the graph is below the x-axis. And just put this note in. So sloppy, sorry. And if you want to sketch this out, that was terrible. So negative 3 square root of x looks something like this. And then from 1 to 4, right, this is the little area we're looking at. Again, below the x-axis is why we got that negative 14. Okay, so got that one almost done. You can see something weird coming here, but first this one, nice and easy. Again, we can use our power rule here. This is one where I would skip some work because I understand what's going to happen, but let's do the work and make it make sense for you. So using our power rule, find our indefinite integral. We're looking at x to the 4th power divided by 4 plus c. Let's evaluate this at 2 and at negative 2 and see what happens. When we plug positive 2 in, we have positive 2 to the 4th over 4 plus c. Minus, let's plug negative 2 in, negative 2 to the 4th divided by 4 plus c. Well, when we raise positive 2 to the 4th and negative 2 to the 4th, we get the same exact results. 2 to the 4th and negative 2 to the 4th are both 16. 16 divided by 4 is 4. So what I get here is 4 plus c, and then a minus 4 and a minus c, so everything cancels, making our area 0. 0 square units, or just 0. Okay? Why do we have an area that zeroes out? Again, this is one where I would not have done any work. And that's because I know exactly what this graph is going to look like. And I'm hoping you kind of do too. So x cubed has symmetry over this interval that we're looking at here. X cubed graph looks something like this, okay, where we have symmetry about the origin. So when we're looking from negative 2 to positive 2, this section of graph here, the area between the curve and the x-axis, and then over here, the area between the curve and the x-axis, those two areas are exactly the same. But one is positive above the x-axis, one is negative below the x-axis, so they cancel out, right? The one here ends up being positive 4, and the one down here ends up being negative 4, and that's why we get a 0. So for me, I would not have done this work, not that it was hard work, right? It didn't take that long, but I wouldn't have done that because I know this graph has that symmetry over symmetry about the origin over that interval. So I know that from negative 2 to 0 is going to completely offset what happens from 0 to 2. So it's kind of nice to know what your graphs look like, and if you're looking at symmetrical intervals, because you can save yourself a little bit of work. Although it's not necessary to have that information stored, because ultimately the work will lead you to the correct answer. Kind of similarly, if I was asked to do like negative 2 to 2 or any symmetric interval there of like x squared, I probably wouldn't evaluate this from negative 2 to 2 because I know what x squared looks like. And I know that over here from negative 2 to 0 that this is going to be exactly the same as this. Now they're not going to cancel because they're both positive, but instead of evaluating from negative 2 to 2, I would just find 0 to 2 and then double it, because evaluating at 0 is always easier than evaluating at some non-zero number. So again, knowing what your graphs look like could save you some work, but it's not completely necessary because the work will always get you to the answer. Just wanted to throw that out there. All right, last one. Last one is a little strange because we do not have an integration rule for absolute values. How do we integrate an absolute value? Well, we don't. We have not learned that. We know if we integrate 1 over x, we get the natural log of an absolute value, but we haven't integrated absolute value. So, if we don't know how to integrate our function, let's see if we can do this geometrically. Let's take the geometric approach. Hopefully we know what this graph looks like. When we graph an absolute value, it's going to make a V shape, and this particular V shape, instead of being centered at the origin, is shifted to the right 2. So you can go to Desmos for this, but I know what this graph looks like already. So we're looking at a V shape, again, shifted to the right 2. So if I go to the right 2, that's where the vertex of the V is going to land. And so we're looking at a graph that looks something like this. And Desmos could confirm this for you as well. So we're trying to find the area that's enclosed under that curve, between that curve and the x-axis, over the interval from -3 to +4. Well, that's this area here, along with this area here, and those two areas are shapes I know how to find the area of. So even though I don't know how to integrate the absolute value function, I can still find the definite integral because I can still find the area. So I'm looking for the area of two triangles, which means I need to know the base and the height of each of these triangles. So the base here is pretty clear. From -3 to 2, that's 5 units, and the base here is pretty clear. From 2 to 4, that's going to be 2 units. But what about the height here and the height here? Well, in order to know that, I have to know this point right here and this point right here. So at -3, where is my function? If I input -3 into my function, -3 minus 2 is -5. The absolute value of -5 is +5. So the coordinate here would be -3, 5, which means we've gone up 5 units to get there. And if I plug 4 into my function, so plug a 4 in here, 4 minus 2 is 2, and the absolute value of 2 is 2. So the coordinates here are 4, 2. That means I've gone up 2 units to get there. So now I have the dimensions of my triangles and I can find my area. So the first triangle is 1/2 times a base of 5 and a height of 5. And then I want to add on the other triangle, 1/2 times the base of 2 and a height of 2. So this is 25 over 2 here. And I know this one reduces, but because I have a fraction and I want that common denominator, I'm going to leave this as 4 over 2 here, right? 4 over 2. And that makes total 29 over 2 square units for my area. Okay, so the geometric approach definitely comes in handy. It's just not always possible, but it's there. Okay, so we're finding the area between a curve and the x-axis over a specific interval. That is our definite integral. Hard to say all that without getting tongue-tied. All right, you should have enough to get going on your assignment, but as always, if you have any questions, please reach out. Until next time, take care.